Yes, dear colleagues and students, I welcome you all to this video lecture. It's very important lecture from chemical engineering point of view. I'm briefly introducing the speaker, that is Professor Ranga Narayanan. He is the UF Foundation Distinguished Professor of Chemical Engineering at the University of Florida. His research is in the area of pattern formulation. He has over 200 published papers and conference presentations, along with 5 authored and edited books. Among his awards, he is the UM University Fellow, Fulbright Distinguished Chief Fellowship, Israel, Senior Scientist, European Commission, Distinguished Foreign Scientist Award from the Government of India, Japan Society Foundation Fellowship, Fulbright Scholar from Belgium, Alexander One Humboldt Fellowship, and many more actually. Many more fellowship. He has many academic fellow also. So with this brief introduction, I invite the speaker to start his lecture, and we will be delivering the lecture on pattern of the divine patterns by design scaling model of fluid patterns.
Oh, thank you. Very generous. Thank you very much.
Yes, it's okay. Fine.
Well, I'd like to thank the audience and Professor Mondal and organizer and Dinesh for arranging this invitation. I promised that I would make this talk entertaining. Most people who speak in chemical engineering, and I'm normally no exception, like to show our latest research with equations and graphs and all those things. Of course, I've been in your position, sitting. So, but I thought that in deference, because I've been in your position, very often sitting in the audience, waiting for the last slide in conclusion, so that I could just go. Okay, I was going to try and avoid that, and I said, let me give a talk with virtually no equations, but talk about the physics and explain in terms that engineers would appreciate. Very often in chemical engineering, all of you or most of you are, or in mechanical engineering, we use the idea of dimensionless groups. And when you introduce a dimensionless group to students, you say, oh, we take the equations and we take a characteristic and we get a group of Reynolds number or Nusselt number. Students shake their heads and they go through it, they say, oh, they only want to know if it's going to appear on the exam. Okay? But of course, why do we introduce these dimensionless groups? And why did engineers introduce them? Because they were interested in building large units, distillation columns, extractors, reactors, right? And they couldn't afford to build huge distillation columns and all things without investing a large amount of money. So in order to make sure it works, you build a small unit in the lab. But then you need to know how to scale it up. Simply multiplying the flow rate by 100 times and having the length of the column also 100 times or the width 100 will not solve the problem. So they begin to understand the physics of mass transfer. The physics of a mass transfer coefficient to the heat transfer coefficient. And then began to say, we believe that there are certain dimensionless groups, scaling factors that remain the same. Whether you have a lab unit or you have a pilot plant unit, and then you go to the complete industry. So this is how we begin to introduce this to undergraduates in separations and so forth. And then of course, this plays an important role even in research, because when you present a paper, you often make it in dimensional terms. Today what I want to do is to bring about that there's something else interesting about dimensional terms, something that we might not have thought about. So I'm hoping that at the end of the 40 minutes or so, that you will go home thinking differently and seeing nature differently. So the talk of patterns of the divine, okay, principally has to do with the patterns that we see in nature. Okay, and patterns by design. The patterns that you can do in the laboratory by emulating nature. And in this, we are talking about scaling laws between nature and what you do in the lab. So that is the general feature of the talk. So I'll start off with the typical patterns that you might have seen. So these are not anything unusual, some are perhaps, but I'll just all the same point it out to you. On the far left are cloud patterns that I took, I'm trying, I forgot where to, but it was roughly, the pilot was saying that we were roughly 35,000 feet above sea level, and the estimate was that we were 20,000 feet above the clouds. Because the clouds were only about 10 to 15,000 feet above ground. Okay? So rather cloudy day there. And you can see without absolutely any doubt, as technologically challenged. Okay, so there you go. Thank you. You can see clearly that there's an organized pattern. Without doubt. It's so uncanny that you must wonder, what is it that nature allows these patterns to be formed? And you see them with all. Here, this was taken by a student who was visiting me on a Fulbright. His name is Jason Picardo. It's an R is missing, sorry, Picardo. Okay, and he was taking this was taken at the University of Florida. He was coming into the department and he saw this flash flood. It was a rainy season. Okay, and he could notice, and we'll see this, that there were these waves coming down. There was not any rich. These were actually natural waves, okay, coming down. And when we went closer, he could see very small waves. So he took a picture of it. This was taken on the beach, not far from where I live, maybe about 100 miles from where I live, on the coast, on the Atlantic coast, by my wife. And she was walking on the beach and she said, and this, by the way, has nothing to do with the waves. Nothing. The wavelength of the waves is quite large, several feet long, okay? But this is of the order of inches, okay, this distance. So they're completely uncorrelated. Yet why do you see these patterns? This is actually from a book by Lucht on vorticity. And this is these are not cracks. This is what you see in a dried lake bed in Ethiopia, near the Ogaden Desert. Okay? And so the lake bed is dried, and what it leaves behind are these tessellations. And these, you can see that these tessellations, you can see from the size of this human being, you can see these tessellations, they are quite large. Okay. Now, finally, this is kind of odd. These are basaltic rocks. They're cuboids. I don't know if you can see them. They're actually cubes, okay, rectangular cuboids, formed millions of years ago, okay, in Scotland. And you find them in a number of volcanic regions. This is not the only place. This is a particular, this is a specific example. That these were formed when the lava began to suddenly and quickly began to solidify. Okay? Very typical. We'll move on to ask, what are these? We won't discuss each of these. We'll discuss some specific examples and maybe others, and ask what is common about these. Are they simply random? And And why is a chemical engineer interested? So we say, why do we study patterns? Maybe they are aesthetically pleasing, maybe. And I'll show a bit of that as well towards the end of the talk. Aesthetics in patterns. Maybe we seek order in life, okay? We want to predict the nature of events. And it's not simply writing one more paper, okay? That there has to be a connection. Or perhaps we can make devices. Typically, chemical engineers want to do something which they think is going to benefit society, okay? Such as better materials with predictive structure, okay? Examples where you might apply this to microfluidics or 3D printing or so forth, okay? So, there's many reasons, but I want us to understand that what we do in the lab is not isolated from what we see in nature. There is a connection, okay? So, let's go here, and actually what you see now, as you get closer, I don't know where this is going. Now it gets really close. When you get close, the patterns behave incoherent. It's only far away that they appear to have structure. Okay? But when you get really close, if you get at the local level, it might seem turbulent and incoherent. But from afar, it looks very nice. You sometimes see that in the rockets that leave. You see the flames that come out. The flames, if you zoom in, you shouldn't go close to it, of course, you will see incoherence. But from afar, you'll see with clear waves. Okay? And we can ask why. What is it that closeness loses that objectivity? Distance gives you a feeling of scale. Okay? So there are clearly organizing patterns involved in this. All to do with ultimately dimensional scales. So we ask ourselves, what causes pattern formation? Now I want to point out that some of these things I'm talking about are my own theories. Some are established, some are my views, and some of my views do not necessarily collaborate with others. So I want to point out that there are alternating views of the same things. Okay? Pattern formation implies that patterns are created from an earlier state. You can't form something unless you form it from an earlier state. So there was an earlier state. And that earlier state can be usually one, maybe typically uniform, without any pattern, coherent pattern. And that state can change its uniformity suddenly to another state in which you get these patterns. That indicates that the first state is unstable. It is the instability of the first state to some event that makes that state unstable and forms another state, and the manifestation of the new state are patterns. Okay? But then what causes the instability? I mean, if you say patterns came because of instability, what causes instability? So we need to ask ourselves, what is the origin of an instability? Okay, so now we know from our understanding of process control, which I'm sure some of you get involved with, that instability arises when disturbances are aggravated by the state of the system. So let's go into that. So there's a feedback of the disturbances which lead to an instability. Now let me dwell on that a bit. So for example, I might have a process, and it may be that I have some low energy inputted to the process, and I give a disturbance, and when I give a disturbance to that process, the perturbation dies, the disturbance dies, because the energy input is low. So this is a process, whatever the process might be. Energy is inputted to the process, it's not enough energy, So when a disturbance is given to the process, it acts in the presence of this energy, but it's not strong enough, and that disturbance dies, and that process is stable. But if I have a process where I have high energy input and I give a disturbance, then that process can lead to one of two things. The disturbance or perturbation can grow catastrophically, or it can grow into a new state. And we use the word, it can saturate to a new state. And the new state into which it saturates will have patterns. Okay? So it can either grow into a catastrophic situation, or it can grow and become into a saturated state where you have patterns. So there's one of two possibilities, but that happens when the system is given high energy. So let's give a specific example. Let me say building blocks. Children always play with building blocks. We love to do that with children. Now suppose you give a small disturbance. Well, that block is nothing's going to happen, it's going to come by. But now suppose you have a tall set of building blocks. You go on doing that. Now you give a disturbance. Now what happens, it falls and you get a catastrophe. It doesn't form a pattern. The whole thing tumbles down. Right? So you're not shocked. But when you start to see, put it in words. I mean, the event is common. We've all seen building blocks. So what I'm saying is not new. But when you start to put it in the idea of the left system had a low energy, the potential energy was low. The right system had high energy, the potential energy was high, it was tall. So the one which had the high energy was susceptible to a catastrophe with even the slightest disturbance. Okay? But not always. When you give a high energy, it need not, in this case the building blocks, it's going to fall. But in another case, in some other scenario, where you have a high energy, you give a disturbance, that disturbance can cause patterns. And then we say, why? Why those patterns? So we go to the next stage, and we are going to slowly build upon what causes these patterns. What is the other rule? Okay, so let me take a simple example of an instability. So I want to slowly transit to the fact that patterns are caused due to an instability. Instability is caused when you have high energy in the system and in the presence of a disturbance. Sometimes that disturbance can lead to a catastrophe. Sometimes the disturbance can lead to the pattern itself. That's where we are in the talk. Okay? Now, but the example, so now I want to go on a little further with this instability, idea of instability, and slowly morph myself into the idea of a dimensionless group. And where does it play a role? So I'm going to show here from the internet, these are the credits that I have, are three flames, Bunsen burner flames, and I'm going to turn on the video, and you're going to see, in a moment, you're going to see that in the left, the flame looks pretty laminar. In the middle, it's a transitioning to a turbulence, and the right, it looks pretty much, very much turbulent. The only difference that we have done here is the flow rate of the gas. Small flow rate. You see that in the lab. Many of you go to the chemistry lab. Sometimes you're fooling around with the Bunsen burner. Slow flame, you'll see a nice parabolic shape. Slightly more, will start beginning to shake. You say, why? Just the flow rate alone. Why did it make it shake so much? We'll see why. Okay? It has to do with the fact that this gas has got to combust, right? And if the flow rate is too high, there's so much of feedstock, so much of fuel, that it cannot burn fast enough. So what does the flame do? It creates more surface area. So the best way for the flame to burn off this gas is to create more surface area. And the best way to create more surface area is to create this turbulent structure. And that's what so it's a competition between flow time and reaction time. So you see, I immediately have two time scales. There's a flow time and a reaction time. And there's a competition between these two. Okay? And this competition leads to a dimensionless case. It's a ratio of times. Okay? Oh, so sorry. Okay? It's a ratio of times. And the ratio of times leads to what we call a Damköhler number. So those of you who are in chemical reaction engineering would have seen the word Damköhler number. The Damköhler number is a ratio of 2 times. Flow time to reaction time, or might sometimes be it might be the reverse. Thank you so much. Thank you. I think. Okay, so that's what. So it's a simple idea, for something we have seen in our chemistry labs. So I thought I'd bring that as an idea. It's a ratio of times. Okay, but we might not have viewed it that way. Once you start thinking and say, "Oh, do I see a pattern?" You begin to really see the pattern here in the transition. That's when you begin to see a wiggly thing. It's only when you really increase the flow that that pattern becomes chaotic. So patterns can become organized, and with further excitation, with more energy, can suddenly become chaotic. Okay? And there are some well-known people who have studied these sorts of patterns. One of them, I will show you his picture, comes from BHU. Okay? Not too far back, that you might be very interested in knowing who he was. So the surprise is there. Okay? We'll show you. Okay? Now, what do we mean by dimensionless? Now, of course, this talk was meant for all people, not necessarily only chemical engineers. So I don't have to tell this audience, but in general, if you ever talk to somebody, talk to your grandparents or somebody else, you want to explain what dimensionless is, they say, what do you mean without dimension? See, in applied physics, dimensions refer to fundamental or derived units, as we know. Force has the dimension of mass times length or times square. The ratio of 2 forces is therefore unitless, is without dimension. Okay? But common people think of dimension as length, but dimension for us can be dimension of time, dimension of force, dimension of energy. The ratio of 2 energies is without dimension. So that's dimensionless, right? So these dimensionless groups, time by time, is dimensionless, as we saw earlier. Is key in understanding the simple pattern that we saw of the candle, or I'm sorry, the Bunsen burner. Okay. Now, suppose I take another one, another example. I'll bring you into these. Oh, let me run this movie again. Okay. This is again from the internet. I'm going to show how a tsunami is caused. A tsunami, just in words, is caused when you have a sudden upset in the tectonic plates, say in the ocean. It need not be in the ocean, but let's say it's in the ocean. The floor of the ocean suddenly moves. Suddenly. It's a lot of energy. And once that moves, that energy has to go somewhere. So what happens? That energy goes, okay, you're going to see. You see the, I hope you can see the back, the sudden tilt. The energy goes in the form of a wave, and that wave has kinetic energy. It's moving at a high speed. And then as it reaches the beach head, it has to stop. That means that kinetic energy has got to be converted to another energy, potential energy. It has to conserve. Okay? Viscosity plays a very small role. So when it comes to the beachhead, it finally becomes a huge wall, and that's the wall that becomes catastrophic. So there is a ratio of two events here. Okay? One is the kinetic energy, the other is gravity. Okay? Or potential energy. The ratio of potential energy to kinetic energy leads to a dimensionless group. Okay? And so we have here momentum or inertia, which has to do with the kinetic energy, versus gravity. That's the balance. And that balance leads to a ratio, and that's called the Freud number. So, if you talk to a physicist, they may not appreciate the Freud number. When you talk to a fluid dynamicist, they'll say, the Freud number. That comes in as a ratio of these two forces. Okay? And that is the ratio that determines this catastrophic effect. So when the fluid number exceeds the critical, you don't get a pattern, you get a catastrophe. Like the first thing that I was saying, okay? Like that building block falling. So this is a case where a pattern is not formed, but where the dimensionless group going beyond the critical causes a catastrophe. In the earlier case, the Damkohler number reaching a critical value causes a pattern. So I hope now you're getting the gist that dimensionless groups, when they reach a critical value, you will form. That means there has to be another very important thing that we have here. What is the other thing? That's my second message. Patterns result from instability was the first message. Competition of energy or forces is important to cause patterns. You need competition. And this is my view. This is not, like I said, this thing about competition is what is my thesis on this. This is my principle that I believe in. And I believe it's really true. There is another view where you can see patterns forming when birds, for example, form a V shape. There it's not pattern formation due to competition, but it's pattern formation due to cooperative signal, cooperation. The pilot bird signals to the bird behind, okay, and they take turns in position to become the pilot, so they can take the major strength. And it's the weaker birds that are in the wake, okay, that they actually go the way. That is pattern formation, not so much of patterns as we saw in those tessellated patterns of the clouds, but cooperative signals. But the patterns I'm talking about are spatial patterns, and they come from competition. This competition leads to a dimensionless group. Competition in time, competition in forces. So, I would hope that when you see a pattern, the first thing that strikes you is there must be two effects that compete with each other. And the competition between these effects is the reason for the pattern, and that's the wavelength that's being selected arises because of this competition. Okay? How are we doing in time? How do you have? Oh, I don't need that much. Okay? Now, so let's go a little further. Now I'm going to say, suppose you take Newton's law, which is simply mass times acceleration is the force, and then you have a balance between momentum and forces such as gravity, minus forces such as surface tension, and frictional forces like viscosity. So if I have a balance between momentum and on one side and balance on the other side between gravity and surface tension, I will come up with a dimensionless group. And one of the most famous dimensionless groups is due to Osborne-Reynolds. And Osborne-Reynolds experiment, this is taken from the proceedings of the Royal Society. This is, in those days they didn't take photographs, they drew them. Okay? So this is a caricature of Reynolds' experiment where he had a fluted tube, and in this fluted tube he put in water, and he then began to put in a little dye, and he began to see, as he reduced the flow rate of the water, he began to see that this dye, as he increased the flow rate of the water, he began to see the flow rate that the dye began to cause a sinuous action. Okay? And so he began to observe this as a function of flow rate and began to ask what is the reason for this sudden sinuous. The sinuous nature is a pattern. I began to ask when does that occur. So I've taken this little, the idea of showing this thing by Gill, okay, and it is, let me go back and show what the experiment is. Sorry. Okay, again. Okay, so we are going to show an experiment here where we have a hydrostatic head and several tubes, and you're just running the water, and it's nothing, it's very, very slow. Now you increase the hydrostatic head, and you start seeing near the top almost just about to break into a pattern, and here more turbulence and so forth. So the idea was, the higher the flow rate, you begin to see this. Of course, we're not surprised. But what is the competition? The competition was clearly inertia that is causing this to move fast, and what is restraining it is the viscous effects. Okay? So inertia which causes the flow or the kinetic energy of the flow versus the viscous effects of the viscous damping, again, a damping force, okay, is the ratio of these two forces is what leads to the Reynolds number. So we have known it this way, but the Reynolds number was simply not some empty-headed number that we go into the lab and say, we're going to get the friction factor of a pipe, okay, some log F versus RE. It's all great. But when we look at it, we should say, it is the reason that you go from a parabolic flow, an organized laminar flow, to the first time a pattern is formed, a sinuous flow. That sinuous flow, that pattern, that wavelength as it is moving is a cause, is a result of the competition between inertia and viscous. Just like in the Bunsen-Burner flame, the origin of the pattern that we saw in the transition is a ratio of two time scales, reaction time to flow time, the Dunn-Kruger. Okay, and just like in the catastrophe of the tsunami was the ratio of inertia to gravity, and that was the Froude number. Okay, the Froude number. Okay, so we have several like these. Now, okay, so I can dismiss it. Now let me go to this one of my favorites. I showed this thing here in the beginning. These are tessellations of a drying lake bed in East Africa. Getting close to it, you can begin to see. Not terribly organized. After all, this is in nature. Somewhat difficult to make it absolutely perfect. But here is a beautiful one of convection cells. So I'll explain why convection cells causes these patterns. I'll explain them, okay? Right now I'm just showing these pretty pictures, okay? But just want to let you know that if you did this in the lab, well, this is what's happening is this. You have water on the lake, the sun is beating down, the lake bed gets hot, okay? Some evaporation takes place, of course. But most of all, there's a density gradient in that film of water. And that causes flow. I'll explain that in a second. That flow, which is a buoyancy-driven flow, okay, generates patterns in largely unbounded space. So here is an experiment of a thin layer of silicon oil, heated from the bottom, from the underside, cooled from the top, and with a shadow graph. Look at the beautiful hexagons. Okay, this is not computer drawn. This is a shadow graph. Okay, and amazing. Now here on the right is a crude experiment. Okay, this is in real time alcohol, ethyl alcohol, with a little bit of aluminum flakes, and in real time, I hope you can see from the back, you will see patterns. Okay? These patterns, if you look at them closely, are actually going to look like those patterns on the left. Okay? They're not as organized as the ones on the top, but they clearly are tessellated. You can see the patterns very, very clearly. Huh? Maybe we need to dim the lights a bit, I'm not sure. But I'll just show this one last time. I won't ask you to do that too much. Yeah, yeah, that's good enough. Yeah, it's okay. Thank you. But you can see, actually, if you dim these in the front, at the top, I don't know. Yeah, that's good enough. Can you see them now? Very clearly, right? Okay. Okay, so you can actually get this. Now, what is the cause of these patterns? There's competition. I said there's competition. So I have here a caricature or a picture argument. I've got a liquid with a gas above, okay, and it's hot and gravity is pointing downward. What happens is when you disturb the interface, okay, locally at the top it's cold and locally at the bottom it's warm, okay, and what happens is hot fluid moves up and comes back down, okay, dragging in hot fluid again. So you've got a competition now between two effects. One is density gradients caused because of temperature gradients, and the other one is the dissipation of the heat due to thermal diffusion and the dissipation of momentum due to viscosity. So we've got two effects. Gravity acts to pull down the more dense fluid. Viscosity and heat diffusion impedes that flow. Okay? Now, you get here. I have temperature differences that cause density and gravity to determine momentum. So I have a balance between momentum and viscous damping, or between momentum and thermal diffusion, and that leads to a ratio of forces leading to another dimensionless group known as the Rayleigh number, after Lord Rayleigh. Okay? So these patterns that you come occur when the Rayleigh number exceeds a critical value. And the Rayleigh number is the ratio of buoyancy on one side divided by viscous damping and thermal diffusion. That's what it is. So, and that's what you see in those patterns seen by Koshmi. Okay? Now, here's a rather interesting example which some of you would have seen in the literature, but this is one that we did in our lab. Okay? Okay, so I'm going to have two cylinders, an inner cylinder, and I'll show you the experiment in a moment. The inner cylinder and an outer cylinder, and between the two cylinders in the gap I'm going to have a fluid. So I'm looking at this from above. This is what you see from the top. Okay? I have two ways of rotating the cylinder. In one case, the outer cylinder can rotate and the inner cylinder can be fixed. In the second case, the inner cylinder can rotate and the outer cylinder can be fixed. Let's say. I'm always going to keep one cylinder fixed, the other moving, not both moving. Now, when the outer cylinder moves and the inner cylinder is fixed, the angular momentum is stratified so that the angular momentum at the inner cylinder wall is 0, but the angular momentum at the outer cylinder wall is maximum, and the fluid is pinned to the outer cylinder wall. It cannot move anywhere. Here, on the other hand, the angular momentum at the inner cylinder is maximum, because that's one that's rotating, and the angular cylinder at the outer wall is 0, so the fluid that is near the inner cylinder wall is flung forward. Okay? So there's a difference in how you do this, and there's a ratio of two effects. You can have a ratio of centrifugal force, I'm talking about the right case, versus the viscous effects. Okay? Whereas the Reynolds number was inertial force versus viscous. This is also inertial versus viscous, but inertia due to centrifugal versus viscous effects. So we're going to run this now. I'm going to run two cylinders. I want to show you what the cylinders are. Okay. Oh, brother, I don't want to do this so fast. Let's stop here for a second, okay? Let me show you what this is. I've got two cylinders. There's a cylinder in the middle, which you can barely see, where my laser pointer is, and there's a cylinder on the outside. The outside cylinder is transparent. It's made of plexiglass. I have two belts. You see a belt there? That belt can move the inner cylinder. This belt can move the outer cylinder. So in my left experiment, I'm going to move the outer cylinder. Okay? That will move the outer cylinder. Okay? Nothing happens. The fluid is in between, it's grey in color, nothing unusual, it's just swirling. Kind of boring. Now I'm going to run the Now I'm going to run the inner cylinder and see what's going to happen. This is the outer cylinder is held fixed. The inner cylinder is moving. Just wait a second. It's increasing speed. Now you see bands. Do you see those bands? These bands are sudden. They happen when the speed went beyond a critical value. Those were bands that are the onset of non-laminar flow. When you had the Reynolds experiment, you had to increase the flow rate. Here I have to increase the speed. Of course, the fluid cannot go anywhere. It's just swirling. So what does it do? It changes. Instead of going round and round, it goes like in a figure 8, like this. And that keeps repeating in bands. So you have separate bands. And these bands are called Taylor Couette, after G.I. Taylor and Maurice Couette. Okay? So this is what you have here, these sort of bands. And they actually can be very useful. We can use this for wastewater treatment of all things, you know. This is really important. We can use this sort of thing, or a bioreactor. Okay? Okay, we're moving on, and I think we're almost towards the end. Two more. This is instability and patterns from resonance, something which Dinesh is interested in. It's a pattern due to Faraday. So I want to point out here, let us say that I have a pendulum that's moving simply like this, or it can move up and down by the base state. Okay? Now I can move the pendulum base rate faster and faster. This is an animation, and suddenly it will become unstable, depending on certain frequency. So we can do the same sort of thing in an experiment, and in this experiment, I'm going to have, it's probably not easy to see from the back, I'm going to have two fluids, a fluid 1 and a fluid 2, and you can barely see an interface there. That interface is not really shifting around. But on the right, I have the same arrangement. I now move this at a higher amplitude, and now the interface begins to undulate. This means that my system frequency is now reaching resonant frequency. When it reaches resonance, the system begins to become unstable, the flat becomes non-flat, okay? And that waveform that you get, and the frequency at which this occurs, the critical frequency, you can make it into a dimensionless frequency, leads to a pattern. So Faraday patterns occur because there's a competition between inertia, which is coming from shaking, and surface tension, which tries to make the interface flat. These are the two competitions. And you can get a variety of modes. Let's see this. Yeah, you can see this. Same system run at different frequencies. Okay? And at each frequency you have different amplitudes at which you get patterns. You can see the patterns are very different. On the right are the patterns that you are predicted from theory, and on the left were the patterns that you actually see in the experiment. Okay? And of course you can keep doing this in a whole variety of containers, and you can see these sorts of unbounded patterns appear. Again, due to dimensional screws. Okay. We're now towards the end, and I wanted to show you, I've done this again, I'm afraid, okay, where I wanted to show a familiar but still not necessarily well understood phenomenon called a balance between gravity and surface tension. So I want to show this by way of a simple thought experiment. Many of you have played with straws. You suck up Coca-Cola and sometimes you put your finger on top, okay, if you have nothing else to do, and then you hold this finger and you see through the straw, you will actually see that liquid or Coca-Cola is being held up. So you put your finger on top. If you let the finger go, it will fall, but not all the way. Okay? If you let your finger go, it will fall, but not all the way. Okay? You will still get a fill, maybe a short fill. Okay? So it's not quite to do with the finger. It just has to do with the fact that the straw is very narrow. If I do the same thing in a test tube, much wider, even though the test tube is closed at the top, this liquid will not remain. It will fall, completely fall. So what's the difference? What's the difference between the left and the right? The only difference between left and right is this is a narrow diameter, it's a wide diameter. But what happens is I have a competition between two effects. Okay, sorry, I have a competition between two effects. One is the surface tension is trying to keep the liquid up. Gravity is trying to cause the liquid to fall down. Okay? Surface tension acts on diameter. When the larger the diameter, the weaker the curvature. So on the right, the effective surface tension is weak. Gravity is great and it falls. On the left, surface tension acts on diameter. Small diameter, greater curvature. So surface tension effect is greater, it keeps the liquid up. It has nothing to do with the In fact, I have my finger. It's closed. The top is closed here also. Both are closed. Okay? But the fact that on the right it falls, from common experience, on the left it doesn't, shows to you that there is a competition with two effects, gravity and surface tension. This leads to a dimensional group called the bond number. Okay? And when the bond number exceeds a critical, the liquid will completely fall. Catastrophe, not a pattern anymore. Okay? So, I am now showing an experiment. This was done by an undergraduate student. This undergraduate student finally became a lawyer. Okay? We have a very clever fellow called Josh Sims. Okay? And I wanted him to perform this experiment at different diameters. He said, no, I'll do it in one setting. So what he did was, he took a conical section like I'm showing here, and he put light oil right here. I think I borrowed it back again. Thank you. Yeah. Okay? No. I'm not sure what I did. Sorry. Okay. Yeah. So he put a conical section here, and he had light oil. So what he did was he kept adding oil here, and of course above this oil he had water, colored water. I'm going to show you the experiment. So as he adds oil here, this interface becomes wider and wider. This bottom interface goes to wider and wider. The water is heavier than the oil. So imagine I have series of wider straws. Now he doesn't need a series of wider straws. He can make this diameter larger and larger by simply adding more oil, drop by drop. It's a clever experiment. Okay, that's why he became a lawyer, I think. Okay, so now we have this experiment on the right. Here you can see the colored water. Okay, and underneath his plate is clear oil. He's added oil on the left. You can't see the left plate. Little by little, and suddenly this water it reaches a critical diameter, it's going to fall. There you go. Okay? So, this is a critical bond number. Okay? Very clever. So, it's due to Bond, Wilfred Bond. Okay? And it actually agreed with the theory, where it's supposed to occur. So, there came another undergraduate student. So, he performed another experiment. And in this experiment, he took glycerine on a glass plate and suddenly flipped it. And you could see raindrops of glycerine falling. And the wavelength that you could see here correlates with what you should see by theory, which of course I have decided not to show. So you can do a lot of these. Another 5 minutes? Yeah, good. Okay, you can see, here's an experiment on Rayleigh-Taylor instability in painting. Okay, so there's a Mexican fellow called Cejeros, okay, and what he did is he put white paint on top of black paint. White paint is heavier than black paint, and after some time he began to see these little spots appearing. Okay? And those spots will remind you of what that earlier experiment of glycerine was. You could see this little thing. So this same thing now, this is white over black. Beautiful, not very organized, but because it's after all a sort of a crude experiment. So this is where heavy is on top of light. But don't think of it that way. This is a paint, this is an actual geographic thing. Remember I said patterns of the divine. Okay? Patterns by design are like what we saw in those simple experiments of Koshmeder, of Faraday, of the one which Josh Sims did. But here is a nature. Do you see those mountains? If you look from afar, the wavelength is pretty regular. This is in Banff in Canada. My wife took this, and at the bottom, right near this one, there was this plaque done by some geological society of Canada. And they said that is squeeze plane. So, alright, you say, how did these patterns form? Suddenly there was a catastrophic event. Suddenly the earth moved. Okay? And when it moved, these waves began to form because the soil was soft. See, if you take a belt, I'm not about to do that, but if you take a belt, I think you might see that if you take a belt, it's somewhat soft, and you move it slowly, you will get a wave. Nothing much. But if you move it suddenly, You will get several waves. That's what's happening. So it's a time constant, ratio of 2 times. The time of the suddenness of the motion versus the relaxation time of the material. Okay? And that leads to something like a Deborah number. Okay? It's again a ratio of 2 times. Okay? So these are the sorts of things you can see. And I don't want to go on. There's several things like this. Scale also has to do with distance. Here's from the book of Baron Black. If you look at this scale from afar, you can't see what's going on. Who is this? But if you actually diminish it, you'll see Abraham Lincoln. Okay? So it's a question of also distance. Like what we saw on the right. So remember I showed you on this one. If you get close, you won't see incoherence. But from afar, it will look coherent. So distance is also important. I have not quite discussed that in detail. That's yet another talk. So the questions that have arisen over time is what generates patterns? What specifies the distance or wavelength of the patterns? In my group, this is what we study. Principally in fluid mechanics, also in heat transfer. How does one study collaborative patterns that transit various length scales, go from one to the other? What selects the type of pattern or geometry? And can patterns suddenly disappear in favor of a catastrophe? These are the questions that we have asked and we continue to answer in part. Okay? And my message is dimensionless groups are not simply empty-headed exercises of converting a large number of parameters to a few. That's one. They are not just empty-headed exercises of going from one thing in the pilot span scale to the full scale. Maybe that is not that empty-headed. That's more important. Okay? But they also have to do with patterns themselves, the dimensionless groups, competition, instability. Okay? And there are names which are associated with that. The famous names that you know start, for example, with Stokes, Gabriel Stokes, G.G. Stokes, Sir Michael Faraday, Lord Rayleigh, okay, the third, okay, the third, quick, okay, and then this person face you might recognize as Alan Turing, okay, who worked a lot on a famous paper, The Chemical Basis for Morphogenesis, which has to do with patterns in nature, like patterns on a snake, patterns on a zebra. Those are reaction diffusion patterns. Again, competition between kinetic effects and diffusion effects. Okay? Then you've got G.I. Taylor, whose experiment, the Taylor-Couette I showed. And then right here, you've got Osborne Reynolds. You have Froude. Okay? Here you have Prandtl, the Prandtl number. Okay? Which is a ratio, again, of two important, not simply thermophysical properties, kinematic viscosity by thermal diffusivity, but more important, it has to do with the time scale of heat transfer versus the time scale of vorticity dissipation. That's the way to look at the Prandtl number. Okay? And then here is should be one that ought to be familiar to many of you. That is Professor Rastogi. A very, 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 very excellent. One of the principles. Okay, who has done a lot of work on the Belousov-Zhabotinsky reaction and done on electrodeposition, also to do with scale. I wanted to show that to you here because he comes from BHE. Okay, and on the far bottom here is Chandrasekhar, S. Chandrasekhar, speaking to Zeldovich. Zeldovich, they had a very interesting thing. Chandrasekhar was an astrophysicist who knew and picked up fluid mechanics. Zeldovich was a fluid mechanicist who picked up astrophysics. Okay, and here's a picture of the both of them in conversation. Both worked on scale. And if you read Chandrasekhar's book on hydrodynamic stability, you will see that he transits scales from the lab to the stars. Okay, so this is ultimately what I wanted to show. You do have such phenomena appearing on seashells. When you see them, ask yourself the question, where does the competition come in? It comes not only in what we see, but patterns are part of our nature. This is a thing of Escher. If you look carefully, can you see how the fish slowly has morphed into the bird? Look carefully. Sky and water. Sky at the top, slowly coming down, okay, and you begin to see how the artist has gone from the fish very slowly. See here, beginning to form the bird. It's a beautiful, it's an imperceptible, seamless way of motion, okay, again of scale. So there are many like this that you can begin to pick up. And we have this, there's a book actually by William Jackson called The Desire to Seek Symmetry or Pattern, okay, Heaven's Fractal Net. And it's very interesting to show that we have a lot of these things in nature, but also in the lab. You know, if you go to many South Indian homes, you see these patterns drawn in the morning. They're called columns. Okay, it's actually drawn in my house years back. And these are patterns. People want symmetry. They want that. You see this in Jerusalem. This is the Dome of the Rock. This spice store fellow had the dome there on Temple Mount. One whole surprise. But he wanted to make it organized. He didn't want to have this some random, block of things. You see this in temples. Okay, you have it in Chittor. This is a Jama Masjid. This is on a cathedral. From afar, it looks very, very organized. When you get closer, you begin to see the various, close-up friezes that you can tell. Okay, these are geometric patterns. And of course, when you get closer, you begin to see the various biblical themes. So this I took in Patan, and from afar you can look at the very organized. When you get very close, you begin to see the various myths and various stories. And this is Talaj also in Gujarat. So I wanted to end this with a story. So this is the last slide. Many of you might have read or heard of a story, and at least I'll repeat it for those who don't know, of a Trivikrama. He's he's seen as an incarnation who was able to make 3 strides. And the story goes like this, just very short, that there is a king who is not really a bad king, but very, very, very egotistical. And he thinks he can give anybody anything. He alone is capable of granting the wishes. So Vishnu comes in the form of a dwarf, almost imperceptibly small, and that's the key story here of scale, and says that he requests something from the king. The king says, what is it you want? And the dwarf says, I want 3 paces of land. So the king very haughtily says, this dwarf, he wants 3 paces of land, and I'll grant it to him. So the first pace, the dwarf suddenly becomes huge, and with the first pace begins to stride the worlds. With the second pace, he strides the heavens. With the third pace, he does not know where to go, and that is when he decides that he must put the third on the dwarf, and here's the dwarf. He has put it on the head of the dwarf to finally grant him salvation. So it shows that scale really matters. Just because it was a dwarf, you must be careful. It can go into large scale and completely change your view of what is about to happen. So I took the same picture. This is taken in Halebeedu in the state of Karnataka. I think ultimately, so I wrote the thing, He Stoops to Conquer, which is actually a novel by Oliver Goldsmith. I wanted to end with this last poem taken from the Rig Veda of the Nasadiya Suttam. And it's a translator by Arthur Basham, who has done a very nice translation. And in this, he says, so we wonder, what is the cause of patterns? What is the cause of all this? So he says, all creation had its origin. Whether he, meaning whether he who is above all, fashioned it or whether he did not. And then he says, he surveys it from all highest heaven. Maybe he knows the reason for all this patterns that we see, or maybe he himself does not. So with this I want to end. I have credits. These are the various people due to whom I really owe. various ideas. What I have presented are actually scientific ideas in a more, hopefully, engaging way, without equations and things like this. But the research that has gone behind this is far more academic, with equations and things like that, as we tend to do as academics. But I wanted to step back and see that there is much more to it. And I hope that you've appreciated it. Thank you very much.
If there are any questions, I think Ranga will be able to answer. Are there any questions?
Surely. Yes.
So, what is your view about chaosness? Like, can I go, like, as you said, like, as I zoom in, my patterns are getting little scattered. So, if I wanted to look from very far to any chaos situation, will I be able to find any patterns there?
Yeah, in some cases you can. Like I was mentioning, when you see a rocket fire, I mean, you've seen launches from Sriharikota, right? Many of us, great pride, look at them, right? But you look at the flames that emerge from the rocket. They're not just gaseous flames. You begin to see the pattern. They actually look really, really. And they are associated with an instability called the Kelvin-Helmholtz instability. But if you go closer to it, you see nothing but chaos. So, even these so-called chaotic events, in some cases, have got organization associated with them, pattern organization associated with them, competition associated that leads to those patterns, instabilities that ultimately lead to themselves. Okay? But chaos itself could be a result of an instability that leads to a pattern that upon further aggravation leads to a secondary pattern, that upon further aggravation leads to tertiary, and these patterns begin to collaborate.
So, multiple competitions.
Yes, like for example, dendrites that are formed in solidification, or as Rastogi has worked on, electrodeposition. Cellular forms grow, very organized, then they begin to merge, like Oswald Ripening, and then they begin to merge, and then they begin to form maybe something more complicated than fingers, and the fingers, the more complicated fingers themselves begin to merge, forming maybe organized dendrites, and then the dendrites begin to merge, forming chaotic structures. So it's repeated instabilities. That's my view.
Thank you. Thank you for the nice speech.
Okay. Are there any further questions? If not, let's thank Ranga for I request head of the department, Dr. Mangal, to give the institute product. Thank the speaker for the talk.
Okay, so it's really fantastic. You'll see the fantastic lecture you'll see on the dimensionless number. We really know that dimensionless number is used for scaling happening in chemical you'll see processes, equipments. But really he explained, you'll see in what way you'll see it is also used in natural phenomena also. Okay. So really fantastic. Okay, good.
Thank you.
Good lecture. Okay.
Oh, beautiful. Absolutely. Thank you. Thank you. Oh. Yes, both. It's a privilege. Thank you. Thank you.
Please come.
Sure.
Okay, will you go?
Okay, so this is the end of the lecture. I think we have some snacks, tea and some snacks.
Please feel free to ask questions. I enjoy questions, and I hope that you will think about, reflect, and ask questions.
Thank you all for
Thank you so much for attending